Hey guys, welcome to the second lesson on asynchronous programming using C#. Today we're going to be talking about tasks. We're going to talk about what a task is. We're going to talk about the thread pool and how the thread pool works. We'll talk about how we can pass data into tasks and how we can return data from tasks. And then we'll finish by talking about the difference between this idea of CPU-bound tasks and I/O-bound tasks. Each of them have benefits, and you have to know when you want to use each. I'm going to try to emphasize and try to explain the concept of, in a client application, the most important thing might be responsiveness for you. So depending on what you're doing, you may have to do some kind of programming that will give you the responsiveness you want, but it may not be the most efficient way, and that could be something to do with I/O. And we'll look at that and we'll talk about what that means. Okay, so let's go ahead and start talking about what a task is. Basically, the best way to think of a task, or the easiest way to understand tasks as we move forward, is you could think of a task as something that just represents an asynchronous unit of work. And basically what that just means is that a task represents an asynchronous unit of work. That means that that unit of work is running while the main thread of execution continues. That's what the definition of asynchronous is. So this idea of a task utilizes the concept of a thread pool. Now, in the last video, I talked about what this idea of a thread is, and we went in and we created a new thread using the thread class, and we looked at how that works. And I explained that creating threads and managing threads, are costly operations. They're not, they're not small things to do. So the problem with just using the pure thread class to create threads and create asynchronous actions was probably not the best way to do it, because creating threads all the time, destroying threads, like I said, is costly. So this idea of a thread pool allows us to basically recycle threads. So we can queue some work up to the thread pool. So we have this thread pool, some kind of data structure, and we say, can I use a thread to do some asynchronous work? The thread pool will say, okay, depending on how much action's going on, you can use this thread. It gives you the thread. Then when you have the thread, you do your asynchronous work that you want with the thread. Then when you're done with it, instead of destroying it, it just sends it back to the thread pool and allows it to be used again in other asynchronous work. So at no time are threads being destroyed. They're just being recycled so that they can be used again, which is more efficient. Now, if the thread pool is under a lot of stress and a lot of people are requesting, or a lot of actions are requesting threads, the thread pool is smart enough where it will make decisions. It will say, oh, we're running out of threads, so many are being used, I need to create some more threads. And the thread pool will do that all by itself. It needs to create more threads, it will. So basically, all we do as the programmer is request threads from the thread pool, and it will manage everything with that, and then we get our time, and then once our operation is done, it gets recycled back to the thread pool. Now, we're going to have an example where we look at, I'll show you that I'm not lying, and that the threads that we get are from the thread pool. And the creators of this task parallel library wanted all asynchronous operations, everything to do with asynchronicity, to be inside of this task. So there are ways that we can force and say, I want it to create a new task instead of pulling one from the thread pool, kind of like we did with the thread class. So we'll look at options like that, even though this is just an intro to tasks. Later down in the videos, we'll do more with tasks. We'll try to look at as much as we can. So we're going to start off with CPU bound tasks. Now, I mentioned in the beginning of the video that we're going to break this idea of task into two separate sections. The first is CPU bound tasks and IO bound tasks. Now, just briefly what they are before we go on. Basically, a CPU bound task means that the operations in the task should be utilizing the CPU the full time, meaning that it's doing some kind of operation where the CPU is working with it and doing something constantly. IO bound tasks are things that are asynchronous, but some of the asynchronous work will be waiting for something to happen. For example, we're waiting for something to read a file, and then once it reads the stuff from the file, then we'll do some asynchronous work with that. But the point is, the time that we're waiting, or let's say we're querying, or we're trying to get the HTML of a web page or something, the time that we're going out and contacting the web server and pulling the web page, that time that we're just sitting there waiting, the thread is sitting there idle. It's not doing anything that requires the CPU. It's just sleeping. It's just waiting there. And the problem with that, and I'll talk about this some more, the problem with that is that we're wasting a CPU or a thread pool thread. We're taking a thread from the thread pool that someone else could be using, and we're just making it sleep. We're saying, okay, once it gets the content of a file, or once it reads the web page, or once a user types in a code. Let's say we're waiting for the user to type in something. While we're waiting for the user to type in something, the thread is just sleeping. It's not doing anything that requires the CPU. So that's an IO bound task, and then we have a CPU bound task. So we'll focus on the CPU bound task for now. And then towards the end, we'll look at an IO bound task, and I'll prove to you, the benefits of properly using an IO bound task and properly using a CPU bound task, and we'll take a look at that. So let's go ahead and start with creating our first task or creating our first CPU bound task. So there are lots, actually, 3 ways off the top of my head I could think of that we can create a task. We can create a task 3 different ways. We'll look at all 3 of them. The first one we're going to start off just to get everyone familiar. But then there's just easier ways as .NET progressed. They just made easier ways to do it, and we'll quickly look at all 3. What are the benefits of each? So the first thing we're going to do is we're going to create a function, an operation that will be passed into this task. This will be our asynchronous operation. So let's go ahead and create it, and we'll call it speak. And speak is simply just going to go console.writeLine, and it's going to write hello world to the console. So this is a standard function right now. This is our standard operation. But we're going to pass it into a task and make it an asynchronous operation. So the first way that we're going to create a task is we're going to go task, then we're going to call whatever we want to call our task, T, equals new task. And inside of the parentheses, we see, for our argument, we see an action. It's requiring an action. And now, in my advanced C# section, I think I go over this in one of my videos in there. An action is just a delegate that says, I want a function that has no return value or return type void and takes in no parameters. Luckily, our speak function follows that, so we could essentially say our speak function is of type action. So I'm just going to go ahead and pass in speak. So that now we created our task. Now to start our task, we're just going to go t.start. Now, some of you may be thinking, this guy doesn't know what he's talking about, because I know this is 95% of the time this is not going to work. Now, with this idea of threads, I didn't explain this in the last video. We have this idea of foreground threads and background threads. Basically, A foreground thread can keep the program running. If a foreground thread is running until it's done, the program will not close or stop. Background tasks, background threads, if they are running and the program ends, it does not matter. The program doesn't care if a background thread is running. It'll just throw it away. So background threads do not have the power to keep an application alive. So by default, without specifying anything, our CPU-bound tasks run on background threads. So if we know this is a background thread, basically what's going to happen is our program is going to start running. Our background task is going to start running from the entry of main. It's going to come here. It's going to start it, but it's not going to stop. It's going to continue on, and it's going to end the program right away because it's creating a background thread. And the background thread is going to be executing this, but because it's a background thread, the program just continues on without doing anything. So let's see what happens. Let's run it. Okay, it showed this time. Let's try it again. There we go. See, okay, that time it did not show anything. Let's try it again. So you believe me, it didn't show it this time. This is why I said 95% of the time. Okay, so of course the first time it would show it. Basically, what's happening is when we start this and the asynchronous operation goes off and it goes to run this hello world, the first time it just so happened that it in time before the program ended, the asynchronous operation ran. Now, this is not up to me. I can't decide when it's going to do that or not because the thread pool has full control. It's whenever the thread pool throws me a thread and it does it. So it just so happened the first time, obviously, to make me look bad, that hello world showed. But let's run it again. Look, now it's not showing. Basically, because the program is starting and ending so quickly, the thread pool didn't have enough time to allocate or give me a thread and to run console.writeLine hello world. So you may be thinking, oh, how can we fix this? Well, a simple thing. Oh, let's just do console.readline. Let's make the program not terminate. But I don't really want to do that. It's not that elegant, and I could do that. Like, watch, if I said console.readline and ran that. Now we see hello world, and every single time I run it, now we will see it because the program is not ending. But I don't want to do that. I'm going to do something else. So let me take that line out again, run it again, and we can see nothing runs. So inside of a task, they have a function called wait. And wait's job is simply once the program flow hits this line, t.wait, the main thread is going to sit there and wait until the operation finishes. So until speak finishes, it won't go past this line and continue. So let's go ahead and add in some dialogue so we see what's going on. So let's go ahead and write waiting for completion. Oops. And then t.wait. And then once that's done, we'll write console.writeLine all done. So let's go ahead and run this and see what happens now. So as you see, waiting for completion, hello world, all done. As you can see, the task starts. Once the task starts, the asynchronous operation goes off. It requests a thread from the thread pool, does what it needs to do. As you can see, before it even says hello world from that task, waiting for completion is displayed because the program continues moving on asynchronously. It doesn't. Remember what I said an asynchronous operation was? An asynchronous operation is an operation that continues to run while the main thread of execution continues. So while it's going off and doing hello world, the main thread of execution continued on and displayed waiting for completion. It then hit t.wait, and it sits there until the thread completes. Once the thread completes, it continues on and displays all done. So let's go ahead and run that again. Should get the same output. Okay. So in this first method of creating a task, as you can see, it requires two statements to create the task and start it. There's two other ways, like I said, to create a task. So the second way is, this is just syntax really. We'll say task t equals task.factory start new, passing in gr action there again. We'll pass in speak. So this will create the task, get the thread pool, thread, etc., starting everything in this one line of code. Let's go ahead and run this. We get the same. This is the same way as creating a task and calling t.start. And then there's also one more way. We can say it just in 4.5, I think, task.run came out. And this does, okay, what am I getting there? Oh, okay. Hold on. We just have to go new. Okay. We're just having a little problem there. Okay, and then this is the third way. Task.run, and we could pass in our action. For these series of videos, we're most likely going to stick with using task.factory.startNew. And the reason that we want to do that is because it allows a more flexible way to configure task options, which we'll see. Like we can do some separate things, like make it a long running task, which we'll do here in a second. So these are the three ways, and so from now on we'll create tasks using task.factory.startNew. We'll use this syntax just because we can configure it easier. Okay. So like I said before, I was saying that when we create a task using start new, start, or run, any of these ways, it gets a thread from the thread pool. So I want to prove to you that we are getting a thread from the thread pool. So let's go ahead and make something that will prove this to you. Okay, so let's go ahead and create a function called what type of thread am I? And the job of this is just to display to the console whether I am a thread pool thread or a custom thread. So let's just go a placeholder thread, and we're gonna say thread thread.current thread is thread pool thread. If it is a thread pool thread, we'll say thread pool. If not, we'll say custom. So that's what type of thread mi does. Now to actually call this, we're going to say task.factory start new, passing in what type of thread mi, and we'll wait. We want to wait so that the program doesn't terminate while it's getting it. So when we run this, we'll see that it says I'm a thread pool thread. Let's do that one more time. It says I'm a thread pool thread. And that means that when we created this or got this thread using the factory, it's pulling the thread from the thread pool. Okay, so that just proves to you that when we use factory start new, run, or any of the ways that we create a task, it's pulling the thread from the thread pool. Now, like I said before, however, there is a way that we could kind of do the same thing that the thread class itself does, where we can make the thread pool create its own thread that's dedicated to this operation, and once it finishes, then the thread gets destroyed. It doesn't get recycled. And we can do that even through the task. And we want to use start new because start new instead of run allows us to pass in these options. So we'll say task creation options long running. And by passing in this argument or parameter saying task creation option dot long running, it allows it says now for this task to create a new thread, and once it's done, destroy it instead of recycle it. So if I run it now it says I'm a custom thread rather than I am a thread pool thread. So now this is a custom thread that will be destroyed. So we can do everything in task. in the task class. That's how they designed it. Every single thing could be done. So if we want a long-running task, we can have a long-running task, or make it to create a new thread every single time. So we could do that in here. Okay, so moving on. So far, we've only talked about creating tasks that the operations has all the information necessary for it inside of the function, where it doesn't need any arguments. Like, we don't have to pass any data into the operation. But there are ways that we can do that. The first way we could do it is, I'm not going to really show that way, actually. I'm going to show it using lambda expressions of how we can pass in data that we need to a function. The reason why I don't want to show it the first way is because most people only use this method of doing it just because it's easier. The compiler does all the dirty work behind the scenes of creating this closure, and because of that, it allows it to be easy to pass data in. So the way we're going to do it is by, like I said, creating a lambda or an anonymous method. So let's go ahead and create our function first, and we'll say private static void speak string words. So we're just gonna display to the console whatever is passed into this speak function. So the way that we're gonna pass data to this is we're gonna say task.factory start new, and then inside of the parameter it's saying I need an action. So we'll supply it an action using an anonymous method or lambda expression. We'll say this, and then we'll say speak whatever we want it to speak. So we'll say hello world. Now, behind the scenes, the compiler is doing all the dirty work, like I say, creating the closure. So creating basically the class that's being passed in, it contains the data that's necessary for this. We just take lambda expressions and do it the easy syntax. The start new takes it in action. So we're supplying it in action, and then the compiler will create the closure for us. So, like I said, this is a function that has no arguments and returns nothing. That's an action using lambda expressions, and we're passing that in. So we're saying, okay, start new, call this function right here asynchronously, and inside of this function we're saying call speak. Basically is what's going on. So basically speak is getting called, and this is how we can pass data into it really easily. So now if I run this, oops, I forgot to wait it. Let's wait it till the program finishes. Hello world. I mean, we can say hello, we can say anything. Hello Bob. Hello Bob is displayed. So yeah, so like I said, to make this happen, it's not magic. The compiler is creating a class that's holding all the information necessary that it does not have or needs for the function, and it builds a class, and that gets passed in, and all this magical stuff happens. If you want to learn about that specifically, just research the concept of closures. And you can figure out some more with some more things with that. Now, there are some problems with closures that I'm not going to go into too much, and you can Google that, dangers of closures. And there's some problems with closures of when it actually the capture point of the data. And if you want to find out more, I would just Google it. But basically, if you're using it in loops and stuff, you just got to be careful with it. And you should also look in C#5. There was some changes to the for each loop with closures, where it actually helps you out with for each loops and stuff like that. So I would go look at it and figure out some cool stuff with that. So besides that, we can pass data into functions or pass them into a task by using lambda expressions or anonymous methods like this. We created an action right here, because if we look at the start new function, it says it requires an action, so we supplied it an action with an anonymous method, and our anonymous method simply just calls speak, and we could pass in as if we were just passing like a normal function call, and the compiler does the work behind the scenes. Oh, if you don't know what anonymous methods and lambda expressions are, I have a video on it in my advanced C# section, I'm pretty sure. So I would go look at that and research that and watch that video first before you come in and do this, because from now on, whenever we pass data into a function or into a task, we're going to be using this method of doing it. We're going to be using lambda expressions. So I would go look at that. Okay, so now that we've looked at passing data into a task, let's talk about returning data from a task. Basically how it works is when a task returns some kind of data from a function, and I'll explain what I mean by this. The task returns a task of the return type. So for example, let's say we have a function called add. Let's say public static int add int x int y. So we have public static int add x y, and we'll return x plus y. It's a very basic add function. To create a task that will do this and return the data, the function to actually call this first, we'll go task.factory start new, our lambda expression, and then we'll call add, let's say, 5,000 plus 10,000, whatever. So this is the call to our function. Now, this start new function will return a task of int. As you can see, if I highlight it, it says task of int, and because our add function is returning an int, this actual lambda expression is now a func. It's not an action anymore because it's returning this add 5,000, 10,000 is returning a value. If you look at my videos, I actually explain that if the lambda expression only has one line of code in it, you don't have to specify the return keyword. By default, this will go off and it will return the value of this by itself, because you don't need a return keyword if there's only one statement. So now if I highlight, you can see it's a func of int. Now it's not an action anymore. So this is going to return a task of int. So I'm going to go task of int t equals task.factory start new that. So now t is going to have my task of int return from my add function. Now the tasks have a built-in property called result that gets the result of the function. Now, a couple things to note with the result property. If you say, okay, console.writeLine t.result, once it hits result, the main thread of execution, or the caller thread, is going to wait there until the result comes in from the task. So if I go, okay, calling function waiting for results. So let's go ahead and run this. So as you can see, calling function waiting for results 15,000. So like I said, the key thing to remember here is when we call t.result, the thread will wait here until the task has finished and the result's there, because how is it gonna print it if there's no result? Okay, so now that I showed you that, let's go ahead and look at another example. So basically we have two operations. We have a sequential chances to win and a task-based chances to win. Let's go look at the code. The sequential chance to win, basically it's just some kind of part of an algorithm for calculating the chances to win in a lottery. It doesn't really matter the details with that. What I want to demonstrate though is we have a sequential one doing it, meaning Part 1 will have to go, then once that finishes, part 2 will start. When that finishes, part 3 will start, and when that finishes, then it will calculate blah 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 on the display. The factorial function, just basic factorial. And then our task-based chances to win creates a task for each part. And we'll do all these simultaneously while the other ones are going on. Yeah. So the reason why we can put these in tasks is because each part doesn't require anything from the other part. So because of that, I can do them at the same time. So I want to see which one is faster. Now, because this is such a small operation, we're not going to see that much of a difference in time, but we should see something. That's what I really want to point out. So the time it function takes in an action, and then it calls the action, but it just monitors it with a stopwatch. With the task-based chances to win, as these finish and they hit the part 1 or the results, the caller thread will wait there until the results come in. And this is important because as we move into more videos, we'll talk about other ways that we can wait for the task to finish and stuff. And it's important to realize that when we use result, the calling thread is waiting. The calling thread stops and waits for that to finish at that point. But there's other ways that we can handle that, and like I said, we'll look into that in more detail as we move through these videos. So yeah, let's go ahead and run this and see what happens. They're both gonna run. It's first gonna do the sequential one, and then and then the task-based one, and let's see which one is faster. This one is running all at the same time, each part, and this one has to wait for each other. So let's run it. Okay, so as we can see, the first one is the sequential one, and it finished in 3 seconds. As you can see, this is the time right here. The second one, which is the task-based one, finished in 1.8 seconds versus 3.2 seconds. So as you can see, the task-based one is slightly quicker. It wasn't that much quicker because it only took 3 seconds for the sequential one. But because we can put each one on its own task, we could hypothetically improve the performance depending on how the scheduler works. Maybe these could be running a little bit faster, which we did see a little bit faster output. So once again, let's quickly the details of this program is not important. I just wanted to show you this is all about returning data from a task. So let's quickly one more time go over that when we call start new and we pass in whatever is being returned there. So factorial, what is the return type of factorial? It's big integer. So the return type of this task will be task of big integer. And then once we have that, we can access the actual data, the big integer, by calling result. So as you can see, result is a type of big integer. And that will get it. That gets the value of the task. Obviously, it freezes the caller at that point. Okay, so the last thing we're going to be talking about in this lesson is this idea of I/O bound tasks. Now, I mentioned this before that a CPU-bound task is a task that should be using the CPU the whole time while it's executing. We shouldn't be sitting there waiting for something to happen. We shouldn't be waiting for, someone to type something or a web server to respond or stuff like that. We should not be waiting for that. That falls into I/O-bound tasks. Now, I have here set up two functions. The first one is download web page, which just downloads a web page based off the URL and gets the HTML. Don't worry about the actual details of that. It does not matter. Then we have download web page async, which simply calls download web page and wraps it around in this task.factory start new and returns that to the caller so that you can get the result and stuff like that. So now the question lies here, is this a good thing to do? Download web page will go off, and because we're calling it asynchronously but wrapping around a task around it, yes, it will work, and yes, it will be asynchronous. But is it efficient? Because if we think about it, while we're waiting for the web page to respond, our text or our thread that we have sitting there waiting for it is simply sitting there and waiting for it. It's not doing anything. It's a waste. It's not efficient. We're taking a thread from the thread pool and making it sit there and idle and not do anything. But as the programmer, you need to ask yourself, what am I looking for? What is the most important thing to me? Is it more important for me to create an environment that is completely responsive and it's not lagging and there's no delays and stuff like that? Then then you have to weigh the benefits and the costs. Maybe I want to wrap this synchronous call just around this test.run or test.startNew. That's completely up to you, but this is not the most efficient way. Now, I'm going to show you a couple things, but as we move along, I'll explain, how we can be more efficient with this. To download a web page, there is actually now built-in asynchronous functions that we can call that are the most efficient. And I'll explain what I mean by that here in a second. Let's just go ahead and run this and see that it works. So what I'm going to do is I'm just going to go task of string download task equals download web page async, and we're going to download. Let me copy and paste this. This is just a 5-second web page that was developed. So this web page will take 5 seconds to respond back to the caller. So that's why we're going to use that, so we can see some kind of delay. So that's our download task. Then inside of it, we're going to set up this little while loop, and we're going to say while the download task is not completed. This is completed is a bool value that checks whether the task is completed or not. So we put into a loop. So while it's not completed, we're going to go console.write dot, I can't type ever, and then thread.sleep 250. Thread.sleep, it's just a pause in the thread. It makes the thread stop for 250 milliseconds, and then it will do another dot. That's just so we can get the dots. And then once that is done, once it breaks out of the loop, then we know the task is done, so we'll write out the result. So download task.result, and we'll write that out. Let's go ahead and run it. As you can see, it's getting the web page, dot, 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 dot. That's what the while loop is doing. Once it did, it gets the HTML and it displays it to the console. Let's do that one more time. Dot, 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 dot. And then right to the console once it gets the result. Now, like I said, this is asynchronous. This is, if I had this application in a UI application, if I had this program in a UI application form, my UI thread would remain responsive and everything would be good. But while that web page is waiting to respond, that thread is sitting there for 5 seconds doing nothing. It can't be used by anyone else. It's there, frozen, unable to be used. Now, is that, you gotta look at the trade-offs. Do you want to do that? I don't know. But there is a more efficient way. So, inside of these web classes, Microsoft has developed an asynchronous function that can download the page asynchronously. And it will use the most efficient ways. Now, what it will do is, it will create a task, and it will say, okay, start the operation. Once the operation begins and there's I/O, it's waiting for it to complete, it allows that thread to be reused. So it goes out, it gives it back to the thread pool, essentially, and it allows it to be reused. So it releases that thread. Once the web server responds back to the client, then it will recreate, or it will get another thread, it will create the task, and then it will continue on that. So with that method, and I'll show you what I mean by that, with that method, it will actually, it's more efficient. While the task is waiting in the I/O, it allows other resources or other things to be using that task or using that thread in the thread pool. It goes from, just wrapping your code in a task.run or start new, which makes that thread sit there and wait the entire time, to then having your thread started off, then release back to the thread pool so that it can be used doing other things while we're waiting for the web server to respond. And then once it responds, then we'll pick up where we left off, get that task, and continue on. So those are the difference between CPU and this. Now you gotta trade off what you wanna do. So in later chapters, I'll explain more with maybe even this example, calling the asynchronous function inside of the web request and stuff. But I need to get into more of the asynchronous, more things. I need to explain more things before I get into that, and I want to confuse people. So we'll talk about that more. So the last thing we're going to do is we're going to look at an example that I created that will demonstrate, or it will show you the difference between wrapping something in a task, like we see here, and actually building the operation like Microsoft did for some things, where it's built asynchronously internally. And we'll look at the difference of how the tasks are created and given back, and we'll see that what I'm saying to you is actually true. And this should help the most for most people. Okay, so here's the code. Basically what happens is we have two functions, two sleep functions. We have sleep async A, sleep async B. Sleep async A is simply taking the thread.sleep, which just takes the current thread and puts it to sleep for a certain amount of time. And we wrap that around a task.run. So basically we have we're creating a new, or we have a thread from the thread pool, and we're just making it sleep for 5 seconds in this case, using the task.run. We're just wrapping around it, because by doing that, it's asynchronous, and the UI will stay responsive and all that stuff, which I'll show you. In sleep async B, this is actually creating this asynchronous operation without wrapping it around a task.run. I'm not going to go into the details of this quite yet. I will in the future. But I just want you to know that this is sleeping for a set amount of time, but it's not calling task.run. It's not just creating a new thread or getting a thread from the thread pool and going off and do that. So this is having an async operation designed asynchronously, and this is just taking it and wrapping it around a task.run. This is like what we did in the last example. We did the task.run around the web call, but Microsoft has an asynchronous web call that's designed using stuff like this, which is more efficient, and I'll show you what I mean by that. So the first time we're gonna call the less efficient one, the task.run, and we'll see what happens. So let's go ahead and run the program. Basically, I click Start Monitor. And this program, I designed this program where basically it just monitors the available threads for us. We have available worker and IO threads. So in our available worker threads, I have 1,022 available right now. When I call sleep, we'll see that it will say start, and then we'll have one less available thread for the entire duration of that 5-second sleep. Once it's over, then we'll get that thread back in the thread pool, and that's what we'll see. So let's go ahead and run that. Let's go ahead, sleep. As you can see, it says start. Look, worker, we lost a thread for this whole 5 seconds. Once the 5 seconds is up, then we got it back. So as you can see, this is what I was explaining to you. While we're sleeping, we're wasting a thread. We have a thread sitting there the entire time waiting for it to finish. Let's do that. Let's run that one more time so we can see how it works. So we start the monitor. Let's go ahead and sleep. A thread is being used. It's sitting there idle. It's doing nothing. It's just sitting there doing absolutely nothing. Some other part of the program could be utilizing that. Once it's done, then the thread gets back to the thread pool. Okay, let's go ahead now and do the same thing and switch it to sleep async B. Now, this is the more efficient way of doing it, not just wrapping around a task, but they're both async, so they both keep the thread or keep the application responsive. So let's go ahead and run this. Let's start the monitor. Now, watch the difference in this. Ready? When I sleep, oh, look what happened. I hit start. No thread is being consumed. It's just sitting there. Boom. So once it's done, once it comes back from the sleep, it utilizes its threads then that it needs, and that's the full utilization. That's CPU bound right there. It's gonna be working at that point. The I/O is done before it creates those threads right here. Then once we're done with everything that they're giving back, let's do that one more time. The main thing to point out here is while it's sleeping, a thread is not being utilized. So it's sleeping right now, no thread is being utilized so other things can use it. And my program is still asynchronous. And once it finishes, it's they get back. So let's go one more time. Let's switch this back to A. So sleep async A. Let's start the monitor and sleep. See, we have a thread sitting there idle, wasting. It's all asynchronous though. Then it's done, it gets released. Let's switch it to B. Start monitor, sleep. Look, no thread is being utilized. This is the most efficient way to do it right here. So the web classes and most classes in the Microsoft framework have asynchronous functions that are designed like this. The more efficient way of doing it. They're not just synchronous operations wrapped in tasks. Even though that makes a responsive application, that's not the most efficient way to do it. They're designed like this at the core. So that's what you need to differentiate, Is it important for your application to be responsive? Well, there's multiple ways you can do that. So don't worry about what you see in this application where you see the async and await keywords. You don't have to worry about that yet. We'll explain what those are eventually. But all I want you to get out of this is just taking a synchronous operation and wrapping it around a task. Although that improves responsiveness, that's not the most efficient way because you're having an idle task the entire time. Designing the operation to be asynchronous at the core is more efficient because you're not wasting a task a thread. So, that's it for this lesson. We'll dive into this concept of I/O tasks more as we go along, because we'll see it most on, like I said, Microsoft Framework classes are designed. Their async functions are designed like this, the more efficient way. That's it for this lesson. Next lesson we'll look at error handling, and I think the lesson after that we'll look at continuations with tasks. So those are the next videos coming up with tasks, and then we'll move on to thread safety, concurrent data structures, asynchronous UI, what else? Async and await, and etc. So we'll be diving into a bunch of async stuff. Now, this video was kind of, here and there. So if you guys have any questions, be sure to let me know, and I will try to help clear them up if you are confused at all. So yeah, be sure to stay tuned for the next videos, and thanks for watching.